Hi again, I'm Rasmus Båth and welcome to this part 2 of a 3-part introduction to Bayesian data analysis, which will go into the why of Bayesian data analysis. If you haven't checked out part 1 yet, I really recommend you do that first. So why use Bayesian data analysis? Why could it be a useful approach rather than using, say, classical statistics? Well, I'm going to give you a couple of reasons. One reason to use Bayesian data analysis is that you have great flexibility when building models and can focus on that rather than on computational issues. Now, if you've done some Bayesian modeling before, this might sound a little bit strange to you, as there are often computational issues when you want to fit your model. What I mean here is that since there is a very clean separation between specifying and fitting a model in a Bayesian framework, you often don't have to focus too much on how your model is going to be computed when you construct it. That means that you can focus on what assumptions are reasonable and what information you should use, rather than on algorithms when doing the actual modeling. And with the many good tools that help you fit Bayesian models like STAN, JAGS and PyMC, there is a good chance that just specifying the model actually is enough if it's not too complicated. So let me give you an example of how easy it is to change a Bayesian model while the computation stays the same. So this is the CEO of Swedish Fish Incorporated, and he's telling us that I've come up with a new, brilliant way of marketing our salmon subscription service. So I guess we no longer have only one method to advertise salmon subscriptions with, and that means it's time to bring back the B in A/B testing. So remember that method A involved sending out a colorful brochure to advertise the salmon subscription service, and when marketing tried this on 16 randomly selected Danes, 6 out of 16 signed up. The new method our CEO proposes, let's call it method B, involves sending out the very same colorful brochure, but this time accompanied by a sample frozen salmon. And marketing has actually already tried this method on another 16 Danes, and this time 10 out of 16 signed up. So what we now want to know is, which seems to be the better method? And sure, there is some evidence that method B is better, but how certain or uncertain should we be that this is the case? So what we want to do is to specify and fit a Bayesian model that helps us answer these questions. This is the model we had before when we just had one advertising method. We drew a rate of sign-up from one prior and ran a generative model that gave us one simulated dataset. But now we have two advertising methods. But the cool thing here is that all we need to do is to copy and paste the one group model. So instead we draw two rates of sign-up independently from two priors and separately run two generative models to simulate two datasets. This is the only change we need to make. To fit this new model, we can use the same procedure as we used before in part 1 of this tutorial, going under the long name approximate Bayesian computation. So here we again first draw fixed parameter values from the priors. This time we happen to draw a sign-up rate of 20% for method A and a rate of 72% for method B. And then we plug these parameter draws into the generative models and simulate some data. This time we got 4 signups for method A and 10 signups for method B. But then we keep these parameter draws only if the simulated data matched the actual data. And this time it didn't, so we're going to filter it away. Sure, for method B the simulated data matched the actual data since we, in the reality, got 10 signups. But it doesn't match for method A, as we in reality got 6 signups there. And we want all the simulated data to match the real data, and therefore these parameter draws has to go. So we do it again. This time we draw some other parameter values, and when we run the generative model this time, well, what do you know? This time we simulate the data that matched. So we're keeping these parameter draws. And now, as last time, we do this whole draw, simulate, react procedure many times, say 1,000,000 times. And what we are left with are two distributions. The distributions of the parameter draws for method A and method B. that made it past the rejection filtering step. Here is this distribution for the rate of sign up for method A, and since it's the probability distribution over likely parameter values that we got after having used the data, it's what's usually called a posterior distribution. It should look familiar to you as it is the same as before when we only had the data for method A. So again, it seems likely that the sign-up rate for method A is somewhere between 20 and 60%, with it most likely being somewhere around 35%. And here is the posterior distribution for method B. And just looking at it, it seems there is some evidence that method B would result in more sign-ups, as the bulk of the distribution is between 40 and 80%, with the sign-up rate most likely being around 65%. But this is just us eyeballing the posterior distributions, and we really would like to calculate some probabilities. Say, the probability that method B do have a higher rate of sign-up than method A. Fortunately, this is very easy to do, as these posterior probability distributions are represented by a long list of parameter draws. So here are the numbers behind the two posterior distributions. I only show the first 8 rows, but there are many more rows in this table. So here, each row is a pair of parameter draws that, when plugged into the generative model, simulated data matching the actual real data. So the way these parameter draws are distributed represents the uncertainty around what the rate of sign-up could be. Now, if we calculate new measures, and we do it separately for each row, then we retain this uncertainty, and the resulting distributions of these new measures can also be interpreted as posterior probability distributions. That is, what is known about these new measures given the model and the data. So what could such a measure be? Well, since we're interested in which of method A and method B gives the highest rate of sign-up, why not calculate the difference between rate A and rate B? Using some R-like pseudocode, it could look something like this. And when applied to each row, it would give us a new column for the distribution of the difference between method A and method B, where a positive number would be in favor of method B. So now we could take a look at this new derivative distribution. Just eyeballing it, we see that it is quite likely that method B has a higher rate of sign-up. Almost all of the probability is to the right of the 0 mark, with the rate B being most likely around 25 percentage points higher than rate A. Again, since we are working with a table of parameter draws, it is very easy to calculate the probability that rate B is higher than rate A. We simply sum up how many draws of the rate difference was above 0, that is, how many times rate B was higher than rate A, and then we divide by the total number of draws. This time we get that 92% of the rate difference distribution is above 0. That is, there is a 92% probability that rate B is better than rate A. To arrive at this probability, we didn't need to change the way we fitted the model. We could use the same method as when we just had data from method A. All we needed to do was change the model and add a prior and a generative model for method B. And then we just did some simple post-processing of the posterior draws using basic arithmetics. So, another reason to use Bayesian data analysis is that it allows you to include information sources in addition to the data. For example, expert opinion. Here is again the CEO of Swedish Fish Incorporated, and he's come to tell us that the sign-up rate has never been higher than 20%, not even in Norway, and it's usually between 5% and 15%. Now, I'm not really sure exactly how much we should trust our CEO. I mean, I think he's smoking tobacco, but I don't know. But for now, let's roll with this new information and see how we can include this expert opinion into the model. Again, this is the model we have so far. I've forgotten about method B for the time being, so now we are back just estimating the rate of sign-up for method A. So how can we include the CEO's information? Well, a natural place to include it is in the prior, what the model knows about the rate of sign-up before seeing the data. What we need to do is to change the prior from a uniform prior which basically says that any rate between 0 and 100% is equally likely, to a more informative distribution that favors values between 5 and 15%. Now, there are many ways to define custom prior distributions. We could stitch together a couple of uniform distributions where we put more probability on the distributions covering 5 to 15%, or we could even draw a probability distribution with pen and paper and scan it in. But often the easiest solution is to use a family of probability distributions that is flexible enough to represent the information that we have, and that we will tweak until it represents that information. For us, a good choice would be the beta distribution. So the beta is a continuous distribution bounded between 0 and 1, which is good because the rate of sign-up can't be less than 0% nor more than 100. It has two parameters, alpha and beta, that allow it to take all the forms depicted here. For example, when alpha and beta are 1, it becomes a uniform distribution. The larger the alpha and beta parameters are, the more heap-shaped and peaked it will become. So here is the uniform distribution we're using right now as the prior for the sign-up rate. A uniform prior is sometimes called a non-informative prior, as it really doesn't contain that much information with regards to what the sign-up rate could be. And here is a proposal for what a more informative prior could be. This is a beta distribution with the alpha parameter set to 3 and the beta parameter set to 25. But the specific parameter values really doesn't matter here. What matters is what shape the distribution has. And here I wanted to capture the information from our CEO that the rate of sign-up usually is between 5 and 15%. So this informative prior puts most the probability between 5 and 15%, but does not rule out the possibility that the sign-up rate could be up to 30%. You could certainly capture the CEO's information in many other ways, but this is what we're going to roll with. So this is our new model. It's the same as before, but now with the informative prior on top. And the cool thing, again, is that we don't need to change the computational part of how we fit this model. We can use the same procedure as before. The only difference is that we will draw the parameter draws from our new informative prior distribution instead from the uniform distribution as before. Here is a distribution you should recognize. It's the posterior probability distribution of the likely rate of sign-up using the uniform non-informative prior. And here is what we got using the new informative prior. Looking at it, it seems that after having used the info from the CEO and the info from the data, it is most probable that the rate of sign-up is between 10 and 30%. So the information in the data pointed to the rate of sign-up being somewhere around 40%, and the CEO stated that it's usually around 5 to 15%. So it shouldn't come as a surprise that the resulting posterior distribution looks like a mix between these two information sources. Now, if we had more data, the information in the prior would have less and less influence. And with enough data, the prior wouldn't matter at all. Similarly, if we had less data, the posterior would look more like the prior. And if we had no data at all, the posterior would be the same as the prior. Now, we are in a slightly confusing situation, however, that we have run two different models and have two different results from the same dataset. And at some point, we should decide whether we want to go with the non-informative prior or the prior from the CEO. But it's totally fine to try out different models and different priors. And it can be worthwhile to try out an informative prior because if you're not using an informative prior, you're leaving money on the table, as Robert Wise puts it. That is, if you're not using an informative prior, you're really leaving out information from the analysis that you have, which seems like a waste. All right, a third reason why Bayesian data analysis is useful is because the result of a Bayesian analysis retains the uncertainty of the estimated parameters, which is very useful in prediction and decision analysis. Here, decision analysis is when you take the result of an analysis and bring it closer to what you care about. Usually you don't ultimately care about the parameter values. What you care about is often things like money and what decision to make to get more of it, or what you could do to avoid different types of loss. We never seem to get rid of our CEO, and here he is again. He asks us, so what should we do? By the way, marketing forgot to tell you that the cost of sending a brochure is 30 kronas, the cost of sending a salmon is 300 kronas, and if a person signs up, we make 1000 kronas on average. Okay, so what should we do? Here are the two methods that we are considering. A, sending a colorful brochure, or B, sending a brochure and a sample frozen salmon. And this is the result we got after having fitted the model with the data from both method A and method B. We did that before, remember? And while this showed that it is probable that method B has a higher rate of sign-up, it doesn't directly tell us what to do, because we're not really interested in the rate of sign-up. We're really interested in which method will give us the most money. And while method B seems to have a higher rate of sign-up, it also involves sending out costly sample salmons. But since we did a Bayesian analysis and we have access to the raw draws behind these two probability distributions, it's very easy to do a quick decision analysis to figure out which method will probably give us the most money. So to the left here, we have the first 8 draws from the many draws that make up these two posterior probability distributions. And the distribution of these draws represents the uncertainty regarding what the underlying rate of signups are for these two methods. And remember that any calculation we perform row-wise here will give us a new posterior probability distribution that retains this uncertainty. So some reasonable things to calculate would here be the expected profit when using method A, which is the rate of sign-up times the 1000 kronas we make per sign-up, minus the cost of sending the brochure. So for the first row, that would be 33% times 1000 kronas, which means we would make 331 kronas on average, minus the 30 kronas the brochure costs. So an expected profit of 301 kronas per sent brochure. And so on for all the rows. And similarly, we can calculate the expected profit for method B, which is almost the same calculation, but now minus 300 kronas for the salmon. And finally, since we're interested in which of these two methods would give the higher profit, we will calculate the difference in profit between the methods, where a positive difference here means method B is better. Just looking at these first 8 rows, we see that 5 out of 8 rows are actually favoring method A. But of course we should look at the profit difference distribution for all the rows. So here we see that there is much uncertainty regarding which method would give the highest profit. It could be that method B is better, but if we count up how many draws are in favor of method A, we actually get that there is a 61% probability that method A would result in better profits. So if we had to decide, this small decision analysis tells us that we should go for method A, even if method B has a higher rate of sign-up. But the main takeaway here should really be that, given the data that we have, there is much uncertainty, and we really would need some better data before making a decision. Alright, so we went from estimated rate parameters to a posterior probability distribution of the likely difference in profit between these two methods. And I hope you saw how easy that was, since we started from the result of a Bayesian analysis, that is, probability distributions represented as a long table of parameter draws. If we instead would have used classical statistical methods like maximum likelihood estimation, we would just have gotten out point estimates, which we wouldn't be able to post-process into something that informed us about the expected profit and that included some measure of uncertainty or certainty regarding the expected profits. But with Bayes, it was pretty simple. So, a last reason to use Bayesian data analysis, but there are many more reasons, but a last reason to use it is because you probably are already. What I mean here is that a lot of classical statistical procedures that you might already be familiar with, such as classical linear regression or the bootstrap, can be interpreted as a Bayesian model with priors and a generative model. And the same is true for many machine learning procedures. And while you don't have to interpret the statistical models you use from a Bayesian perspective, it helped me better understand what many statistical procedures actually do. Not least was a Bayesian perspective super useful for me when understanding how mixed models and hierarchical models worked, which are simple and straightforward from a Bayesian perspective, but slightly mysterious from a classical perspective. So, that were some reasons for why to use Bayesian data analysis. Let's look at some reasons for why not to use Bayesian data analysis. So, maybe everything is working fine as it is, and you're just happy with your tools and your workflow. Then you might not need Bayesian data analysis. Or maybe you're not that interested in uncertainty. There are many good machine learning tools that just give predictions, but with no indication of these predictions' uncertainty. And if you want that, maybe you don't need Bayes. Or maybe Bayesian statistics is too computationally demanding. Maybe you would want to fit the Bayesian model, but your dataset is so large it just takes too long time. Or maybe you just feel that Bayesian statistics take too much work to set up. Even if you would want to try it, the cost-benefit situation doesn't allow it. These are perfectly good reasons not to use Bayes. And what I wanted to say with this slide here is that Bayesian data analysis is just one tool out of many in your data science tool belt. And while it can be a very useful tool, it's not the be-all, end-all of data analytical methods, even though it's sometimes presented as that. So, that concludes part 2 of this 3-part introduction to Bayesian data analysis. If you want to try out what we talked about here, you could go back to your solution to the exercise in part 1 and change it according to the CEO's request. That is, try adding an informative prior to the model, change the model so that it can accommodate data from both method A and method B, and you can also try replicating the decision analysis where we looked at the expected profit of each method. However, if you try this, you could run into some trouble. Because when you add the second data source to the model, you might find that it takes a really long time to run. That's because the method we used to fit Bayesian models in part 1, approximate Bayesian computation, was conceptually simple but also extremely slow. So in part 3 of this introduction, I will give you some hints on how you can do speedy Bayesian computation. And especially we will look at a useful tool called Stan. But for now, I'm Rasmus Båth, and thanks for staying with me to the end.